this third part of membrane transport is really to talk about how water moves. We've been talking a lot about the electrical, chemical forces that act on molecules, but now we're going to talk about how water kind of differs from that. And we're going to explain the difference between osmolarity and tonicity. Our second objective will talk about polarity of epithelial cells and how we have absorption and secretion taking place across the epithelial membrane. So when we speak about osmosis, this is the movement of water through a permeable membrane. It's usually passive, always passive, and it's going to be unaffected by the membrane potential. So whereas we saw, for example, solutes like sodium and potassium being influenced by the separation of charge in the membrane, here we don't see that. Water is not affected by the electrical driving force. It's always according to its gradient from high concentration of water to a low concentration of water. And we can kind of see that illustrated up here. So in the first part of this illustration, part A, we see that there's a high solute concentration inside the membrane. We've got pure water moving from the area of outside the membrane inside the cell. And that's because water is moving from an area where it's highest in concentration, what happens to be outside the cell, to an area where it is lowest in concentration, which happens to be inside the cell. So from 55 moles to 0 moles, and that's the gradient across which water moves. But what we can also see is that water is going to move opposite to the solute concentration. So whereas we have 0 solute outside the cell and solute inside, we see that water is moving from an area of low solute concentration to high solute concentration. So water moves down its concentration gradient, but against the solute concentration gradient. And I want to point out here that this membrane must be impermeable to the solute that's present. In the second part of the diagram, we also see water moving, but it's moving in the opposite direction, but it's also according to its gradient. We've got a solution outside this cell that has 1 molar of sucrose dissolved in it. That gives it an overall osmolarity of 1,000, which is much higher than the internal osmolarity. And so we see here again, water is moving from low solute to high solute, or from high water to low water concentration. So that's how water always moves, okay? As far as the difference between the mole versus the osmole, when we talk about osmolarity, it's the total solute concentration in a solution. So all the dissolved particles in that solution are what contribute to the overall osmolarity of the solution. So we can have 0.1 mole of glucose. If it's dissolved in a liter of water, the overall osmolarity of that solution now becomes 0.1 osmole. But if we have a substance like sodium chloride, we have the same amount of sodium chloride, so 0.1 moles of sodium chloride. If that is dissolved in 1 liter of solution, then the overall osmolarity is now 0.2, and that's because sodium and chloride will now further dissociate into individual particles. And so what I really want to stress here is that the mole is the number of particles, but if that is further dissociated in solution, that is what contributes to the osmole. So the osmole is the total solute concentration of a solution, which takes into account all the dissolved particles in that solution. So we can have 1 mole of sodium chloride dissociate to give us an overall osmolarity of 0.2 in 1 liter of water. In our physiology, we usually talk about a fraction of a mole. So we talk about the milliosmole just because our osmolarity is really just a fraction of 1 mole. And so we usually use the milliosmole to represent the overall osmolarity of our physiologic solution, our body solutions, our plasma, and so on. As far as osmolarity, we're always talking about the ICF versus the ECF. So the 300 milliosmole is what the ICF compartment looks like relative to the ECF, okay? Similar to the membrane potential. Remember we talked about the membrane potential? It was the inside of the cell relative to the external cellular environment. And so as we speak about osmolarity, we can talk about three different states of a cell. So let's say we have a normal eukaryotic animal cell and we suspend it or we place it into a solution of 100% water, pure water. This is normal. This is an isoosmotic solution. We don't see any water movement because both areas inside the cell as well as outside the cell have the same osmolarity. And so there's no fluid movement from one compartment, one area to the other. In a hyperosmotic solution, we see that the cell has a higher water concentration than the outer environment, right? Because the outer environment has more solutes in it. And so we see water moving from inside the cell to outside the cell, which is according to its own gradient. And that creates this crenated cell, which shrivels up, and that's not good, right? That's gonna throw homeostasis off balance. That's gonna result in things like vomiting in terms of the physiologic consequences that we'll see. When we have these hyperosmotic solutions around our cells will shrivel up and they will die, but that's not, so that's not a part of what we see with our physiology, but it can be seen in external states. So if we talk about a hypoosmotic solution, if we insert one of our cells, let's say it's in a Petri dish, we insert one of our cells into a hypoosmotic solution, we'll see water moving in the opposite direction. It'll be moving, again, from high concentration outside, we've got this pure water, into the cell where we have more solutes dissolved, and that will actually cause our cell to swell and eventually rupture or lyse. So again, not good for our physiology. But we can see this happen in some extreme cases. But what we really want are isoosmotic solutions within our physiology suspended around our cells. This now brings us to talk about osmotic pressure. So osmotic pressure is the pull exerted by solutes on water, and it's reflected by the total solute concentration in that solution. And it really ties back to that gradient that I talked about. The fact that water is moving down its concentration gradient, but then it's going to be moving opposite to the solute concentration. And so we can say here that the solutes are exerting an osmotic pull on the water, and they're basically pulling water to the side that has the higher solute concentration. Okay, and we can see that shown here in this image. So side one has a solute concentration of 300 milliosmoles, meaning that 0.3 moles of particles are dissolved in the solution. It has a water concentration of 55.2 mole, and then an osmotic pressure of 7.4 atmospheres. So this is how we represent the osmotic pressure using atmospheres as the unit. Side two, on the other hand, has a higher osmolarity, meaning more solutes dissolved. So an osmolarity of 500 milliosmoles. It has a water concentration that is lower, so it has 55 moles for the water concentration. And it has an osmotic pressure of 12.3 atmospheres, meaning that water is not going to be pulled, water is going to be pulled to this side where we have that higher solute concentration and that lower water concentration. So the pulling effect, the force effect of water moving from side one to side two is what we refer to as the osmotic pressure or the osmotic pull. And so the pull is going to happen according to the osmotic pressure gradient. So if you've got an osmotic pressure of 12.3 atmospheres on side two and an osmotic pressure of 7.4 atmospheres on side one, then we now have an osmotic pressure gradient from 12.3 to 7.4, which gives us movement from side one to side two. Okay. Now this brings us to speak about tonicity. So tonicity differs from osmolarity because it is really only taking into account the impermeant solutes in the solution. And what that means is that while tonicity is also a similar gradient, it only looks at the solutes that cannot move across the membrane in question. okay? Osmolarity looks at all the solutes present in either solution. So we can also talk about a hypertonic solution, which has an osmolarity greater than 300, or a hypotonic solution, which has an osmolarity less than 300, and then an isotonic solution has an osmolarity that is the same as our cells, or 300 milliosmoles. To kind of drive home the point of osmolarity versus tonicity, let's talk about this solution here as an example. We can have a solution that is initially isoosmotic, but is not isotonic. And to kind of explain what that means, let's look at this example here. We've got a cell, and we've got 300 milliosmol as the internal osmolarity. We've got 300 milliosmol as the external osmolarity, so the solution in which that cell is suspended. And so we have an isoosmotic scenario happening here, right? We've got 300 inside and 300 outside. But if we look a little bit closer at the actual solutes, the outside compartment has urea. The inside compartment has a solute that cannot cross this membrane. Urea can cross the membrane. The solute in purple, we're calling it an impermeant solute, meaning that it cannot go across the membrane, or that the membrane is impermeable to that solute in purple.